Good afternoon, everybody. My name is Jonathan Wankombe. I'm a junior computer science major currently attending Southern Methodist University. Today I'll be showing my presentation I've made regarding my research topic, from game engines to the battlefields, software dependability in military and defense systems, under the umbrella of Dr. Eric Wong, Shi Wei Su, and Zhao Chen. This was through the UTD Software Dependability Centric Application Research undergraduate research program, which combines my interest in game development, artificial intelligence, software engineering, and defense technology. Core of my project is this question: can we use powerful, real-time game engines, like Unreal Engine, not for entertainment purposes, but to test and enhance the reliability of AI systems, use in military drones, and the possibility to other autonomous systems of military use and defense use? My focus revolves around AI-controlled autonomous drones, simulated fall injections, and system robustness testing. In addition to my project, I've also been composing a research paper along with it that explores and highlights both the technical and ethical implications of using entertainment software in high stakes defense environments to highlight different facets and instances of this application. Throughout this presentation, I'll walk you through the background, methodology, technical contributions, and key findings from my simulated drone missions using AirSim and Unreal Engine, as well as what I learned through the entire research program through fault injections and dependability modeling. To provide viewers a better comprehension on this topic and my research project in general, I will speak on some background information that will clear things up for y'all and give y'all more context regarding my project. I think we are all familiar with the context of war and the aftermaths that follow it. As time goes on, militaries and militias around the world have always looked to gain whatever slight advantage they could since the ascension of warfare. This is the reason these forces have always made it imperative to further the researching and also the technological advancements in defense and various other weapons and weapon systems. A recently highlighted technological advancement in into military technology has been use of autonomous weapons and vehicles. A consensus most popular of all of them in most recent conflicts has been the drone. As seen in a lot of recent global disputes, such as the Russo-Ukrainian War and the Israeli-Palestinian conflict, drone warfare has been an important factor in the outcome of various encounters and battles. Along with being cost-efficient and easy to make and access, drones are one of, if not the most, versatile technologies of the 21st century with a wide range of use of application beyond just military use. Some of these uses include agriculture, infrastructure, and security, and much more. Regarding more specific military uses, the drone is applied in is in surveillance, logistics, strike mission teams, and electronic warfare, and much more. Another unorthodox technology militaries have been used to implement in contemporary times is the use of game engines to enhance the application of weapon defense systems. The game industry has expanded itself as a stakeholder at the top of the global market, signifying its importance. In contemporary times, the game engines have been the backbone of the creation and development of 2 and 3D games. A gaming engine is essentially a framework that consists of designated tools, pre-built functions, features, and libraries that are used to improve the process of developing a game. Many militaries have been previously using older combat simulation frameworks to test their weapons, vehicles, and systems. A lot of these frameworks were rigid with poor accessibility and limited graphical modeling that would hinder the development of use of military assets. Due to the limitation of these existing combat simulations, military groups have been looking to implement these game engines in replacement to their old simulation systems and frameworks due to faster, cheaper, and more advanced development environments. Game engines like Unreal, Unity, Godot, and much more provide modular, real-time frameworks that are continuously updated, tested, and capable of handling complex visuals and interactions. Purpose behind my research. The research is important due to the rapid rise in the use of game engines in different militaries that still have components in many layers to research on and build upon as is a newer practice. In most military contexts, testing AI systems, especially for autonomous drones, is done mostly in lab environments or through mostly costly real-world prototypes. These methods often can lack immersion and real-time behavior insight, making it difficult to predict how systems perform in dynamic or hostile conditions. With the implementation of game engines, this dynamic changes. Additionally, hardware-based testing is expensive, risky, and hard to scale for edge cases. Game engines is a new paradigm that supports rapid iteration, meaning developers can tweak logic, inject faults, and observe outcomes without resetting hardware, or risking actual equipment while simulating. This research also bridges the domain of different technologies, allowing for further innovation. Another one of my big points of motivation for my project stems from the growing challenges in modern defense. As we shift towards using AI-driven autonomous systems, especially the drones, the need for reliable, fault-tolerant software becomes mission critical. Military drones operate in highly uncertain conditions, in environments, combat zones, GPS-denied areas, or rapidly changing terrains. If something goes wrong with the software, like a sensor glitch, communication lag, or even like a logic error, consequences could be severe, even fatal. Traditionally, testing these systems has been expensive, hardware limited, and slow to iterate. This lets us explore what happens not just when things go exceptionally right, but when things go exceptionally even wrong, even which is more important. This research isn't about building a drone simulation, it's about creating a dependable testing platform for future military software and showing how game technology can help strengthen national security systems. A methodology. As I was brainstorming and planning my project, I felt that if I really want to maximize my opportunity to learn and challenge myself in this research program, I would just not detail my conclusions just through my theory and others' findings in research regarding research, but actually make a drone simulation testing fall objectives myself. I decided to build my simulation with Unreal Engine due to its extensive functions, vast library, and programming implementations of C++, which I'm somewhat familiar with regarding my past courses in computer science, being C++ courses in object-oriented programming and data structures algorithms. As I commenced my project, I attempted to create my drone environment, which is my level or world in my engine, from scratch to allow myself more control regarding the functions and the makeup of the simulation. As I got further through my project, I came to the realization that I needed to implement an outside source in multiple regards to my project to help alleviate the workload of the project due to my time constraints of the program, even if it meant giving up some control as a developer, which is something that most developers have to come to terms with in the real world whenever they find actual real experience. Um, this is where I started to research and stumbled upon Microsoft AirSim, a discontinued framework developed by Microsoft that simulates vehicle dynamics and sensor systems and also allows for the safety, code review, testing, advanced simulation, and AI capabilities that are uniquely available in a commercial product. In C++ and Python, I programmed and modified custom and pre-existing scripts for my simulation objectives, which is to define waypoint missions, inject control software faults, and log telemetry and collisions as I'm running the simulation. I tested this through various flight missions with known randomized faults and research randomized faults. Technical contributions. In this slide, I'm going to go more in depth on my technical contributions, focus on building my flexible simulation framework that supports both autonomous navigation and fault testing within the game engine environment. First, I implemented an autonomous waypoint navigation system using the AirSim API. The drone can follow a sequence of 3D waypoints defined by the user with varying positions and elevations. This allowed me to test control logic in different spatial conditions. Second, I developed a custom fall injection system. This included simulated jitter, artificial delay, and random positional deviations that mimic real-world issues like sensor noise, lag, or hardware instability. These faults are injected into specific windows of time during flight to observe the AI behaviors under stress. I also built a logging and telemetry system that captures key metrics such as position, accuracy, collisions, and response time during the during the flights. This data helps analyze how faults affect mission reliability. Finally, I designed the mission system to be modular and configurable, so I could adjust the complexity of the mission, add or remove faults, and visualize drone behavior frame by frame. This lays the foundation for future work involving perception-based AI and more advanced reliability modeling. Here's the one of the mock, well not mock, prototype scripts in Python I use for my fault injection system in my fault which mode delay and jitter systems. As you saw in my previous script, there's AI logic regarding a rule-based AI system, which to manage the drone behavior during the faults, I implemented a simple but effective rule-based AI system. The system keeps the track of internal states like fault counts and collision attempts using memory variables. Based on these conditions, the drone can alter its behavior, such as retrying a failed waypoint or skipping a segment after multiple collisions. While basic, this structure demonstrates how AI memory and logic can influence mission reliability and lays the groundwork for future learning-based AI implementations. This is my next slide regarding, this is my next slide consisting of my actual visual of the simulation video. I hope y'all enjoyed that video of my simulation and found it somewhat interesting as well as educational. As you can see by these pictures that I just did not simulate in one environment. I had simulated multiple environments to test my drone to see how it works just on the different how it works on different platforms. And yeah, as you can see, there's multiple environments I tested on, mimicked real world environments as to the best of my ability. Give the drone um, a real world feeling as it's in the simulation. If you notice that the three cameras were at display at the bottom, these are the sub windows, which are implemented with the purpose of capturing images during the simulation or training data purposes for either AI or computer vision. If you notice in the top left corner, different messages were printing on the screen. The collision count signifies the amount of times the drone comes in contact with another object in the environment. The fault signifies whenever a fault is detected, and it signifies the type of fault it detected, severity of the type, and if it's a jitter fault, the duration of the artificial delay injected simulated, um, which is which simulates a real time operation delay, such as GPS signal lags, sensor processing bottlenecks, communication latency, CPU hiccups, or software hangups in the embedded systems. The delta values with these jitter faults and the corresponding logs represent the artificial offsets applied to the simulated jitter faults, signifying how far off the x or y coordinate was jittered depending on the sign, and their log representing the final destination of x or y after their offset was injected. These values simulate GPS drift, sensor errors, or unstable navigation, which are common fault scenarios in real autonomous systems. This slide also highlights the results in the insights captured through my mission logging system, which is record detailed data in structured CSV files during each simulation run. For each mission, the logging system automatically documented key events such as their waypoint transitions, fall injections, position updates, collisions at a higher resolution. Each row in the CSV represents a snapshot of the drone's state, including its position coordinates, whether a fault was active, the type of fault injected, and any corrective behavior triggered by the AI logic. This format allowed for efficient post-analysis using Python, C++, and spreadsheet tools. I quickly identified patterns such as repeated drift during the fault windows, delays in waypoint arrival, or spikes in collision retries. The structured nature of the log also made it easier to compare multiple missions side by side, assess performance trends, and isolate key moments where fault tolerances either succeeded or failed. The CSV will also track internal variables like total faults and collision retries, which gives visibility into how the drone's decision-making process evolved throughout the missions. This kind of granular timestamp data is critical not only for visualizations and diagnostics, but also for informing future improvements to the rule-based logic and underlying control algorithms. Ultimately, this logging system turns the simulation into a testbed for dependability, letting me ask not just did the drone reach the destination, how did it behave under pressure, and why, and how we can the implications behind it. This slide presents two visualizations, which are two of my charts and graphs that I made that highlight the effects of fall injection on the drone's performance during the simulation. On the right, we have the line graph showing position error over time, broken down by fault type. As you can see, the baseline flag with no faults maintains relatively low error throughout, but when faults like jitter or artificial delay are introduced, the error increases noticeably, especially to mid to late phases of the mission. This illustrates how fault compounds over time and disrupts the drone's ability to stay on course. On the left, the 3D trajectory plot shows a visual comparison of the drone's flight path under fall injection. The intended trajectory is smooth and it follows the planned waypoints, while the actual path, especially for under fault windows, shows deviation, instability, even moments where drone slows down, or stalls. Together, these graphs help validate purpose of my simulation. They test how software faults manifest in real-time behavior and to measure how AI-controlled drones respond when things go wrong. This insight is crucial for improving fault-tolerant mission planning in future autonomous defense systems. In this slide, it showcases the messages I had implemented my script for the printing while my simulation was running, showcasing the update, giving me updates and showcasing what is occurring during the simulation, such as the jitters and the severity, as you can see in locations I implemented in, and whenever the simulation was done. Projecting on my simulation work, I've been writing a research paper titled Simulating Fault Tolerance in AI-Driven Drones Using Unreal Engine and AirSim. In this paper, I highlight more than just elements regarding my own simulation. I build upon previous papers and previous researchers' prior work, which other researchers who develop fault detection frameworks using failure mode databases for drones, and also who propose Bayesian fault injection as a method for testing autonomous vehicles in reliability in unpredictable environments. Were those papers focus on either were those papers either focused on data-driven fault modeling or ML-based probabilistic injection? My work just explores more than just that, as also while similar dependability testing can be modeled through rule-based AI and high-fidelity simulation environments, specifically by using a game engine to inject faults and observe how autonomous drone adapts or fails. Another major component I focus on in this paper is the ethical implications of using civilian entertainment in military applications. While Unreal Engine and AirSim were not built for defense, their power and flexibility raise important questions all researchers suppose. What responsibility do developers have when their tools are repurposed for military use? How can we ensure transparency and accountability when simulating combat environments? And where do we draw the line between innovation and escalation? These questions are especially important as autonomous systems gain greater decision-making power in mission-critical settings. My paper argues that the researchers must approach this space not just with technical rigor, but with ethical clarity and understanding, ensuring that tools we build or adapt are used responsibly and with full awareness of their dual-use potential. By connecting real-world failure mode research to immersive modular simulation, my work contributes a flexible platform for both technical experimentation and ethical inquiry in next-generation military software systems. Lessons and challenges. Working on this project has been both technically challenging and personally transformative. One of my biggest hurdles was integrating all the components of the system: the Unreal Engine, AirSim, custom Python and C++ scripting, and logging infrastructure into a single stable workflow. Spent a lot of time troubleshooting issues like simulation crashes, misaligned waypoints, bash scripting, API consistencies, environment inconsistencies, which setting up and injecting faults in a controlled way require precise timing and debugging, especially since minor delays could create major deviations in flight behavior. I also encountered limitations in the document and had to experiment heavily to fully understand how different modules interacted. But those challenges just pushed me to become more resourceful. I learned how to break down complex problems into smaller pieces. I also learned how to read and adapt technical documentation and how to develop my own tools when existing ones did not meet my requirements and fell short. I also deepened my understanding of system software engineering, object-oriented programming, and how AI, control logic, and real-world physics come together in a simulation. On a more personal level, this project taught me to value resilience. There were moments where progress stalled or things just broke unexpectedly with no explanation, I felt like. But learning to preserve and debug systematically gave me a stronger sense of confidence and motivation, not just as a developer, but as a researcher as well. Ultimately, this experience has strengthened my technical foundation, sharpened my critical thinking, and confirmed my passion for creating tools that not only work but matter. Broader impact. Defense and aerospace industries can, in with a broader impact, defense and aerospace industries can implement this with pre-trained AI logic before field deployment, simulate ethical boundary testing, testing lower costs of hardware testing. The academic impact. It encourages the interdisciplinary learning between game development, software engineering, and ethics. Digital direction after the program of my project. Looking ahead, there are several exciting directions I plan to explore to extend this research. First, I want to integrate AI perception systems, specifically computer vision models that allow drones to recognize objects, terrain, or obstacles using onboard cameras. This would enable more adaptive behavior, especially in unpredictable environments where pre-programmed waypoints may not be sufficient. Second, I plan to scale the simulation to support multi-drone coordination. By simulating multiple autonomous agents, I could test swarm behaviors, formation flying, and distributed fall handling, all which are relevant in modern defense and disaster response scenarios. Another key goal is to compare my simulation results with real hardware data. This would help validate accuracy and transferability of the faults and behaviors I observed in the virtual environment. I also aim to refine my AI control logic by integrating machine learning models, possibly reinforcing possibly reinforcement learning or adaptive rule-based systems to replace or augment the current rule-based approach I have in my scripting. This could allow the drone to learn optimal responses to faults through trial and error. Finally, I'd like to package the system into an open source toolkit for researchers and engineers working on autonomous systems. The goal to the project is the goal is to provide a reasonable platform for fall injection, mission logging, AI testing, especially for those who may not have access to expensive defense grade simulators. In short, I see this project not as an endpoint, but as a launchpad in the future for deeper exploration in AI reliability, autonomous coordination, ethical design of critical systems. And I want to give a shout out and acknowledgement to Dr. Juan, Kevin, and Zal for helping me throughout this project and giving me their guidance and advice, and the rest of the REU group for help and then just support and just a fun time in general. I did not take the experience for granted and just want to give my gratitude as I say thanks. And I am Jonathan Wankombe, UTD REU undergraduate research student currently attending Southern Methodist University, and thank you.